Today, let me continue with motion in a circle. We will discuss uniform circular motion and then non-uniform circular motion. We will investigate the difference between circular motion and projectile motion. Finally, we will finish with relative velocity. So today we have three important topics. During the last lecture, I have explained more or less the main principles of this type of motions. So today it will be easier for you to understand. And if you will have any question, please let me know. So let's start with the uniform circular motion. Here we have a circle, perfect circle. It has certain radius and the car is moving along this circular path with constant speed. This term is very important, constant speed. So then this motion is called as uniform circular motion. If the speed is constant along a circular path, then this motion is an uniform circular motion. So what we have in uniform circular motion, we have constant speed, only the direction of the velocity changes. So the direction of the velocity here like this, and here like this, here like this. So the direction of the velocity changes, but the magnitude of the velocity is constant. Speed is constant. And we have acceleration from path to the center of the circle. Okay, we have discussed this one during the last lecture. Let me repeat here something. It has certain radius, and here we have velocity v and we have velocity v. So this is v1 vector, this is v2 vector. Let's consider that v is constant. It means that v1, the magnitude of v1 is equal to the magnitude of v2. But what do you see here? The direction of v1 is different from the direction of the v2. So if you try to calculate delta v, which is given by v2 final velocity minus initial velocity, right? So what is this? This is vector subtraction. So by subtracting these two vectors, you can calculate the delta v, right? So now let's try to calculate delta v. This is the direction of the v1 and its magnitude v1, and this is v2. They have same magnitude, but they have different directions. Then this is the delta v, okay? And the direction of the delta v and the direction of the acceleration are same as we have discussed during the last lecture. So for this reason, for any moment, the acceleration is from path to the center. So here we have acceleration from path to the center, and then here we have acceleration from path to the center. And if you consider velocity, same velocity, then the acceleration is from path to the center. Okay, this is uniform circular motion with a constant speed. Okay, in uniform circular motion, speed is constant, and then we have acceleration, which is perpendicular to the velocity, and it goes to the center of the circle. Do you have any question here? Actually, I have discussed all these things during the last lecture, but I wanted to repeat them here. Then let me continue. So let's consider that again we have a circular path, but now the speed is not constant. The car is speeding up. Okay, here we have a car, we have a circular path, and the car is speeding up. In this case, we will have this type of direction for the acceleration. this goes to the center of the circle, let's say, and acceleration is not parallel to this normal here, okay? So acceleration has this type of direction, and then acceleration has two components. One is perpendicular to the velocity, okay, along the center of the circle, and the other component here we have parallel to the velocity. You see, if the car is speeding up. So another information from the last lecture, this velocity is always tangent to the path, okay? Don't forget this one. So now component of acceleration parallel to velocity changes car's speed, okay? So what do you see here? We have velocity direction, we have acceleration direction. Since they are in the same direction, the car is speeding up in this direction. And here we have another component of acceleration. Component of acceleration perpendicular to velocity. This changes car's direction, okay? This velocity direction always changes, okay, due to this component of the acceleration. Do you have any question here? Okay, then let me continue with the car is slowing down along a circular path. So this is the direction of the car. It is going with some certain velocity, but it is slowing down. So then the acceleration direction is like this. It has two components. One is perpendicular component to the velocity. It changes the direction of the car, the direction of the velocity. And here we have a parallel component, and this parallel component changes car's speed, okay? So what do you see here? This is the direction of the velocity. This is the direction of the parallel component of the acceleration. Since they are in opposite directions, the car is slowing down, okay? Any question here? Then let me try to calculate acceleration for uniform circular motion. Here we have uniform circular motion with constant speed, okay? These are not uniform circular motion. Only this one is uniform circular motion if speed is constant, okay? Now I would like to calculate what is acceleration in uniform circular motion. Here we have two figures, okay? Listen carefully, very easy. You know this information from geometry, very easy. Here we have a circular path, and let's consider this is the initial position of the car, initial velocity of the car, second position of the car, second velocity of the car, and they are equal to each other because we are talking about uniform circular motion. The speed is constant at point P and at point 2. And this is the delta S displacement along this circular path, okay? This is the displacement along this circular path, and this is the radius of the circular path. This is also the radius of the circular path. And what do you see here? The distance from the position 1 to the origin is equal to r, and the distance from position 2 to the origin is given with r, right? And this is the delta phi. So the total phi is 360 degrees for this circular path, but here we have delta phi, very small angle, and this is delta S, very small displacement for a very short moment, let's say, okay? So what do you see here? A triangle, delta phi angle. This is the R, this is the R, and this is delta S. And here I have V1 vector and V2 vector. Just take them and calculate delta V. So this is V1 vector, this is V2 vector, initial and final velocities. And from the geometry rules, this angle is also equal to the angle here in between, right? So here we have delta phi, and this is V1, this is V2, and here I have delta V, okay? The change in the velocity. So look at these two triangles, delta phi, V1, R, delta V, delta S, okay? By using the ratios of corresponding sides of similar triangles, then I can get this relation, delta V over V1, delta V over V1 is equal to delta S over R, delta S over R. Okay, then if I take delta V from this equation, then finally I can get this relation, V1 over R times delta S. So what is average acceleration? Average acceleration is given by delta V over delta T, right? So instead of delta V, just take this one, which we have calculated here, put it there. Here we have V1 over R, delta S over delta T. Now I would like to calculate instantaneous acceleration. This is average acceleration. So what about the magnitude of the instantaneous acceleration at point P1, for example? Then I can write instantaneous acceleration with limit delta T goes to 0. Instead of delta V, just use this expression, and here we have delta T. So what do you see here? V1 over R times delta S over delta T, okay? We have just take the limit of this term when the delta T goes to 0. So V1 is constant, right? It does not change, velocity does not change. R is constant, and then I can take them out, so I can calculate limit delta T goes to 0, delta S over delta T. So what is delta S over delta T? This is the, look at delta S here. Delta S is displacement, right? Along the circular path, displacement over delta T. So what is this? This is velocity, right? So then here I have V1, here I have another V. So V1 times V. So what is V? What is V1? So we are talking about uniform circular motion, and velocity does not change. It is constant. So I can write that V square. V is the speed of the object. It never changes in a uniform circular motion. So here I have R. So finally, this instantaneous acceleration can be written by V square over R. This is the magnitude of acceleration. But here I put radial, you see, A radial. This is the instantaneous acceleration, but here I use A subscript radial. So what is the meaning of the radial? Radial means from the path to the center of the circle, okay? This is the radial. So instantaneous acceleration is given with this magnitude V square over R, and its direction from the path to the center of the circle. This is A radial, and don't forget this formula in your calculations. It will be very, very helpful, okay? And this is valid for uniform circular motion. Do you have any question here? Then let's continue. For uniform circular motion, again, the speed is constant, and we have A radial, okay, acceleration. What is the effect of this A radial? This A radial changes the direction of the velocity, okay? In uniform circular motion, speed is constant, magnitude of velocity is constant, but its direction changes, okay? So it is due to this radial acceleration. So for uniform circular motion, the instantaneous acceleration always points toward the center of the circle like this. It is called the centripetal acceleration. Centripetal acceleration. So then the magnitude of this acceleration we have already calculated in the previous transparency. A radial is given by v square over r. This is the radius of the circle, and then this is the velocity of the particle. And I can write this radial acceleration within another form. So let's consider that the period t is the time for one revolution. So what is one revolution? Bir devir. So you started from this point and you are going with constant speed along this circular path. And then you finished one revolution, okay? So how long does it take to finish one revolution, okay? So this is called as period. And it is time, of course. So how to get relation between a radial and this period? So here I have formula x is equal to v times t, displacement, velocity, and time. So what is the displacement here? You start from this point and then you go around the circle and then you finish your travel here. So what is the displacement? Displacement is given with the circumference of the circle. Circumference of the circle, 2 pi r, right? Instead of x, you can use 2 pi r, circumference of the circle. Then v is this one, velocity of the particle is traveling here in this circle, and then time for one revolution, okay? If you take v from this equation, then you can get expression for the v in terms of t, 2 pi r over t. This is the period, time for one revolution. Here we have a radial. A radial is given with v square over r. So instead of v, just use this v here and then take square of it. And finally, we have a radial is given with 2 pi square r over t square. So what we have here, r is the radius of the circle and t is the time for one revolution. Sometimes in the questions, v is not given, velocity is not given. It is just given in the question that the motion is a uniform circular motion, okay? And v is not given, just only radius is given. Then acceleration is asked. So if a period is also given within the question, you can answer the radial acceleration. You can calculate the radial acceleration. So this formula is sometimes helpful. Do you have any question here? Then let me compare the uniform circular motion and projectile motion and velocities in uniform circular motion and projectile motion. So what we have in a uniform circular motion? In uniform circular motion, velocity is constant, okay, for every point around this circular path, right? And the velocity is tangent to the path. In addition to that, we have a radial acceleration towards to the center of the circle for each point, okay? And due to this radial acceleration, the direction of the velocity changes, okay? Acceleration has constant magnitude, but varying direction. So look at this one. The magnitude of the acceleration is constant. It does not change because it is given by v square over r. Radius of the circle is constant. Velocity is constant in uniform circular motion. So radial acceleration, magnitude of the acceleration is constant, but its direction is always from the path to the center of the circle. For this reason, direction changes. You see, acceleration is constant, but its direction changes. Velocity and acceleration are always perpendicular. What do you see here? This is the direction of the velocity, this is the direction of the acceleration, and they are perpendicular to each other. So here again, they are perpendicular to each other. Here again, they are perpendicular to each other. Okay, this is the direction of the velocity, and radial acceleration in uniform circular motion. Now let's have a look the direction of velocity and acceleration in projectile motion. So what do you see here? We have acceleration in projectile motion. It is given by gravity and it is constant at every point. In addition to that, its direction is also constant, okay? In projectile motion, the direction of the acceleration does not change. But here in uniform circular motion, direction of the radial acceleration changes, but its magnitude is constant. Here, both magnitude and direction are constant in projectile motion. What about the velocity and acceleration? Here, they are always perpendicular to each other in uniform circular motion, but in projectile motion, the velocity and acceleration are perpendicular only at the peak of the trajectory. So here, they are not perpendicular, they are not perpendicular, they are not perpendicular, they are not perpendicular, okay? So these are the main differences between projectile motion and uniform circular motion. Do you have any question? Then I would like to continue with examples from the book. Let me read the question. An Aston Martin V8 vintage sports car has a lateral acceleration of 0.96 g. So g is given with 9.8 meter per square second. So 0.96 g means that you multiply g with this number, and then finally you can find the acceleration of this Aston Martin, 9.4 meter per square second. So this is the maximum centripetal acceleration the car can sustain without skidding out of a curved path. If the car is traveling at a constant 40 meter per second, about 144 kilometer per hour. So remember the units in the first lecture. This is in meter per second, this is in kilometer per hour. Okay, you can convert this unit to this one. So if the car is traveling at a constant 40 meter per second on level ground, what is the radius r of the tightest unbanked curve it can negotiate? The car is in uniform circular motion because it is moving at a constant speed along a curve that is a segment of a circle. So this is the constant speed. It is given within the question, okay? If it is constant speed, it is very nice. Then you can apply the rules for the uniform circular motion. So then what we have here, radius of the circle, radius of the path is asked. Then we know that this A radial is given by V square over R. Let me write here, A radial is given by V square over R in uniform circular motion. Okay, so if you take R from this equation, then you can get this expression V square over A radial. Instead of V, just use 40 meter per second and take square of it. And A radial is this one. Where is it? 9.4 meter per square second. So don't forget, in some questions, instead of meter per square second, the acceleration can be given in G, 1G, 4G, okay, 5G, okay? So then you have to do this math here. So now let's have a look. The result is 170 meter. Here we have meter square per second square. Here we have meter per second square. So this second square will cancel this second square. And here we have meter square. Here we have meter. The final result will be meter in terms of unit, okay? So this is the radius. Now let's have a look. Another example. Passengers on a carnival ride move at constant speed in a horizontal circle of radius 5 meter, making a complete circle in 4 seconds. So here period is given, okay? making a complete circle in 4 seconds. What is their acceleration? So here, period is given, radius is given, but velocity is not given. Only it says that speed is constant, okay? So it is uniform circular motion, but I don't know the velocity. So if I don't know the velocity, how to calculate this acceleration? Radius is given, but velocity is not given. Then I can use another expression for the acceleration, which I have shown you in the previous transparencies. Let me go back. Here we have radial acceleration in terms of velocity and radius. Here we have radial acceleration in terms of radius and period, okay? So now we don't have velocity, we don't have the information about the speed, so I have to calculate the acceleration. What is their acceleration? So the A radial is given with 4 pi square times r over t square, square of the period. Period is given 4 seconds, and radius of the carnival ride is also given 5 meter. Then radial acceleration is 12 meter per square second. The result is in meter per square second. This is the unit for the acceleration, but you can also convert this one to the g. It is higher than 1g. 1g is 9.8 meter per square second. So if the question asks that what is the acceleration in g, then you have to convert this meter per square second to the g by using the relation above. Do you have any question here? Maybe in evaluation there is very nice information. I should also talk about this. So here within the question, acceleration is asked. So what about the velocity? For example, we know that the velocity is constant here because it is uniform circular motion. So then it also asks that what is the velocity? In order to calculate the velocity, you can use this relation which we have done in previous transparencies, 2 pi r, circumference of the circle over period, time for one revolution. Then you can also calculate the velocity, okay? And you can use this velocity here within this radial acceleration formula. So let's consider that you have forgotten this formula, but you remember this one. It is also easy to remember this one. Then you can calculate velocity and then put this velocity in the radial acceleration formula. Then you can also get the same result, 12 meter per square second. So now we have non-uniform circular motion. As I told you in the previous transparencies, if the speed varies, the motion is non-uniform circular motion, okay? Then there are two components of the acceleration. As we have discussed during the previous transparencies, let me go back. Here, for example, this is non-uniform circular motion. So here we have acceleration direction like this. So we have two components of acceleration. One is parallel to the velocity. The other one is perpendicular to the velocity. This is the A radial, okay, changes car's direction. This is A tangential. Here again, if the car is slowing down, this is non-uniform circular motion. Then I have this type of acceleration, and it has two components again. This is A radial, this is A tangential. Okay, now let me come back here. So if the motion is non-uniform circular motion, then the radial acceleration component is still A radial is equal to V square over R. So here we have radial component, radial component, radial component, and radial component. So let's consider that here the car has the slowest speed, and then it is speeding up, okay, along this path, and it reaches its maximum speed here, and then its speed is slowing down, and it reaches again the minimum speed, okay? So here we have speeding up behavior, here we have slowing down behavior, okay? So now let's have a look. This one. Here, the particle is speeding up, and then acceleration is not along the center, okay? We have two components of the acceleration. One is a radial toward the center of the circle, and the other one is a tangential, which is parallel to the velocity. Due to this a radial, the direction of the velocity changes on the circular path. Due to this a tangential, the car is speeding up, okay? And here, look at this one. The car has maximum speed here, and then it is slowing down. Here, the car's speed is slowing down. So now we have acceleration, which is not showing the center of the circle. It has two components. One is a radial toward the center of the circle, and we have a tangential component of this acceleration. Since the car is slowing down, the tangential acceleration direction and velocity direction are opposite to each other. So the car is slowing down, or particle is slowing down, okay? So these are the radial and tangential acceleration. Radial acceleration changes the direction of the velocity, and tangential acceleration increase the speed of the car or decrease the speed of the car. Do you have any question related to the non-uniform circular motion? Then let me discuss the components of acceleration. So here we have radial component of the acceleration. Radial component of the acceleration is given by v square over r. We have already calculated this one. What about the tangential component of the acceleration? It is given by the magnitude of velocity over dt. So here we have velocity. You have to take time derivative of its magnitude. Okay, so look at this equation. Here we have v. Let's consider that this velocity is constant. Velocity does not change. We are talking about uniform circular motion, and since it is constant, the time derivative of a constant number is 0. Tangential acceleration will be 0, okay? In uniform circular motion, since the velocity, since the speed does not change, then this term will be 0, and we have no tangential component of the acceleration. Okay, now let's discuss the difference between these two relations, uniform versus non-uniform circular motion. Here we have two quantities. This is the tangential acceleration. Okay, and what is this? Are they same or different? No, they are not same. This is the tangential acceleration. This is the magnitude of the acceleration. So here we have A, you see, A is given with dv over dt, okay, time derivative of the velocity. So if you use these symbols, then you are talking about the magnitude of radial acceleration, and magnitude of the radial acceleration is given with this term. But this one gives us the tangential acceleration. Let's consider that the speed is constant. In uniform circular motion, if you take the time derivative of the constant number, then it will be 0. But in uniform circular motion, it is true the speed is constant, but the direction of the velocity changes. For this reason, this is different from 0. Okay? But look at this equation. If you put here magnitude of velocity, and if you take the time derivative of this one, when the speed is 0, this tangential acceleration will be 0. This is the caution from the book. Very important. Okay, so this one here is given with a radial if the velocity is constant, and then it gives us v square over r. But in uniform circular motion, there is also a tangential component of acceleration. So then the total acceleration in case of non-uniform circular motion has two components. And these two components can be used here to calculate the magnitude of this acceleration. So read carefully this part from the book, and if you will still have problems, let me know. Okay, now let's see the very nice example of non-uniform circular motion. Here you see a roller coaster cars, and there are many passengers. Okay, so here the velocity is minimum, and then it is speeding up, and the velocity is maximum here. Okay, and then it's slowing down. So this is non-uniform circular motion you can consider, right? So there are large accelerations during the traveling at high speed around a tight loop. Okay, the last topic of this chapter is relative velocity. Very important topic. Be very careful, then you can easily understand. I will talk about the relative velocity in 1 dimension and also in 2 or 3 dimensions. So now let's have a look. What is relative velocity? The velocity of a moving body seen by a particular observer is called the velocity relative to that observer, or simply relative velocity. Here, there are air show planes from Turkish stars. What do you see here? They are flying together, right? And they have velocities relative to each other, and they have velocities relative to the air. They have velocities relative to the ground, okay? If there are observers on the ground. So in this type of shows, the pilots face a complicated problem involving relative velocities. They must keep track of their motion relative to 3 parameters. So relative to the air, to maintain enough airflow over the wings to sustain lift, okay, to keep their position in air, and also relative to each other to keep a tight formation without colliding. Any mistake can cause colliding in between, and then a relative to their audience to remain in the sight of the spectators. So this is very nice example of the relative velocity. So I will go into detail now. Here we have very simple example. What do you see here? There is a cyclist, A cyclist. It is at rest. And then here there's a train, B is the train. And let's consider that the train is moving in this direction. And there is a passenger within the train, and she is moving in this direction. Okay, so now I have questions. What is the velocity of train relative to the passenger? What is the velocity of the train relative to the cyclist? What is the velocity of the passenger relative to the cyclist? So you can ask this type of questions. Here, there is very important information from the book. I would like to read this part and discuss with you. A passenger walks with a velocity of 1 meter per second along the aisle of a train that is moving with a velocity of 3 meters per second. What is the passenger's velocity? It is a simple enough question, but it has no single answer. As seen by a second passenger sitting in the train, let's consider there is another passenger here. She is sitting, okay? And then, according to the passenger sitting within the train, this passenger is moving at 1 meter per second. A person on a bicycle standing beside the train sees the walking passenger moving at 1 meter per second plus 3 meters per second, the velocity of train, So this is the final velocity of the passenger relative to the cyclist. An observer in another train going in the opposite direction will give still another answer. Let's consider there is another train and it is moving in opposite direction with velocity of 3 meters per second. Then what is the velocity of this passenger? Okay, so there are many answers to this question. What is the passenger's velocity? So we have to specify which observer we mean, and we speak of velocity relative to a particular observer. So velocity of this passenger relative to the cyclist. Velocity of this passenger relative to the train. Okay, velocity of this passenger relative to a girl sitting within the train. So this is very important. Each observer, for example, cyclist here, an observer, equipped in principle with a meter stick and a stopwatch, forms what we call a frame of reference. So if the observer is a cyclist, then this has certain frame of reference. If the observer is train, then this has certain frame of reference. Do we have any question related to this part? I will continue with examples. Okay, so relative velocity in one dimension. We continue. If point P, this passenger here, point P, is moving relative to reference frame A, reference frame A is this one, cyclist. So P is moving relative to reference frame A. We denote the velocity of P relative to frame A. Velocity of P relative to frame A. It is given with this expression, velocity of P passenger relative to the cyclist. Okay. If P is moving relative to frame B, train, and frame B is moving relative to frame A, cyclist, then the x velocity of P relative to frame A, which is given with this expression, the velocity of passenger relative to cyclist is equal to velocity of passenger relative to the train plus velocity of train relative to frame cyclist. Okay, so how to write this equation? How to get this one? Here I will show you different frames of reference. This is the frame of cyclist frame. This is the origin of the cyclist frame. This is the x-axis and this is the y-axis. Okay, so the cyclist is at rest at the origin of this frame, and this is the train's position, and this is the train's frame, xb, yb, and this frame, the frame of train, moves relative to cyclist with this velocity. Okay, this is the velocity of train relative to the cyclist frame. And then here there is a passenger. Okay, this is the position of passenger in both frame, in the frame of the train, in the frame of the cyclist. Okay, and this has certain velocity. So here, if you are looking for the velocity of passenger in the frame of cyclist, then you have to write these two velocities, velocity of passenger in the frame of train plus the velocity of train in the frame of cyclist. Is it clear? Any question? So now let me go into detail a little bit related to this velocity. So here, what is this? Let's consider that the cyclist is here and train is here and it is moving. So this is the distance between train and cyclist, let's say, the position of the train relative to the cyclist, this one, x b over a. And here we have passenger within the train, and this is the position of the passenger relative to the train frame, okay? And if you would like to find the position of the passenger relative to the cyclist frame, we have this one. The position of the passenger relative to the cyclist frame is given by xba plus xpb, right? If you take, this is the position, this is the position, this is the position. So we have this relation. If you take time derivative of this one, if you take time derivative of this one, if you take time derivative of this one, then you will get velocities, right? Time derivative of position displacement gives us the velocity. So relative velocity along a line. So what we have here, velocity of passenger relative to cyclist is equal to velocity of passenger relative to the train, velocity of passenger relative to the train plus velocity of train relative to the cyclist. So this is a rule for relative velocity in one dimension. Do you have any question here? So this velocity is written by using this reference frame and by using this derivation. Okay, now let me give you one example, very simple question from the book. Relative velocity on a straight road, you drive north. This is the compass, north, east, south, and west, okay? And then you here, and there is a track here, and this is Earth. You drive north on a straight 2-lane road at a constant 88 km/h. So you have constant speed along the north. A track in the other lane approaches you at a constant 104 km/h. So this is the velocity of track from north to the south. Okay, find the track's velocity relative to you and your velocity relative to the track. How do the relative velocities change after you and track pass each other? So you are moving along this direction, track is moving along this direction, and how do the relative velocities change after you and track pass each other? So now you are here and track is here. So what are the relative velocities? And treat this as a one-dimensional problem. Very simple question. So this is the velocity of u relative to Earth. This is the velocity of track relative to Earth, okay? But we are dealing with the velocity of track relative to u and velocity of u relative to track. These are the questions. So the solution, first of all, you should define an axis. Here, the positive x direction is chosen along the north. Okay, this is the positive x. And what else? So then your x velocity relative to the Earth is plus 88 km/h. This is the Earth frame, and this is your frame, okay, origin of u. So here there is a velocity of u relative to Earth, okay. You are moving in this direction, this velocity of u relative to Earth along the x direction. The track is initially approaching you, so it is moving south, and its x velocity with respect to the Earth is this one, which is given in the question. Since we have chosen this direction as positive x, it will be negative because it is moving along the negative x direction. So the velocity of track relative to Earth is given by minus 104 km per hour. So now let's have a look. What is the velocity of track relative to Earth? It is given by velocity of track relative to U plus velocity of U relative to Earth. Okay? Or you can take this one to the left side, then we have this one. Velocity of track relative to U is equal to velocity of track relative to Earth minus velocity of U relative to Earth. So here we have minus 104 km per hour minus 88 km per hour. So the result is minus 192 km per hour. So this is the velocity of track relative to U. Okay, this is example from the book. I will not go into detail. Then let me continue with the relative velocity in 2 or 3 dimensions. We would like to extend relative velocity to 2 or 3 dimensions by using vector addition to combine velocities. This term is very important. By using vector addition to combine velocities. So if you are dealing with relative velocity in 2 or 3 dimensions, using vector addition will help you a lot. Don't forget, okay? We will have some examples I will show you. So here we have a cyclist. It is at rest. It has frame of A, and then there is a train B, frame B, which is moving with 3 meters per second velocity. And then there is a passenger here. In the previous example, passenger was also moving parallel to the train, but now passenger is moving perpendicular to the moving direction of the train, okay? So passenger is moving along this direction with 1 meter per second. Now, let's use the vector addition, okay? Using vector addition to combine velocities will be very helpful in relative velocity in 2 or 3 dimensions problems. So here we have cyclist frame. This is the cyclist frame. This is the origin of the cyclist. This is the XA, this is the ZA, this is the YA, this is the cyclist frame. And here we have train frame, YB, ZB, XB. This is the origin of the train, okay? And here we have passenger, position of passenger in both frames. So this train has velocity relative to the cyclist. Velocity of train B relative to A cyclist, okay? So this frame is moving along this direction relative to the cyclist frame. So now here we have a position of passenger in both frames. So what is the position vector from the origin of train's frame to the position of passenger? The position of passenger in train's frame is given by position vector R of passenger relative to train. And what about the position of passenger in the frame of cyclist from origin to this position of passenger? Position vector of the passenger relative to the cyclist frame, right? And what is the position vector from the origin of cyclist frame to the origin of the train's frame? This is given by R, the position of the train's frame B relative to the frame of cyclist, okay? So we have 3 vectors here. One is this one, the other one is this one, and the other one is this one. So remember the vector addition, remember the vectors. Here we have one vector, and here we have another vector. So this is the head of first vector, this is the tail of second vector, head to tail, and this will give us the resultant vector, right? So then I can write this position vector like this, RP relative to B plus RB relative to A. So by using the vector rules, I can write this one like this. And I know that velocity in 3 dimensions can be written in this form, dr over dt, time derivative of the position vector, right? So take the time derivative of this one, take the time derivative of this one, take the time derivative of this one. Finally, relative velocity in space in 3 dimensions can be written like this. Velocity of passenger relative to the cyclist. Velocity of the passenger relative to the cyclist is equal to velocity of passenger relative to the train, velocity of passenger relative to the train, plus velocity of train relative to the cyclist. Velocity of train relative to the cyclist. Okay, so in order to find the relative velocity in 2 or 3 dimensions, vector addition will be very helpful. Do you have any question here? Okay, now let me continue. I have 2 examples and then I finish my lecture. So, an airplane's compass indicates that it is headed due north. So, it is flying towards north. And its airspeed indicator shows that it is moving through the air at 240 km per hour. This is the speed of the plane, airspeed. Speed of the plane relative to the air is given 240 km per hour in north direction. If there is a wind from west to east, what is the velocity of the airplane relative to the earth? So this was the velocity of plane relative to the air, and the question asks what is the velocity of plane relative to the earth. So what do you see here? This is the velocity of plane relative to air, and this is velocity of air relative to earth. And the question asks this one. So this is one vector, this is another vector. If you apply head to tail method, you can find resultant vector, which is the velocity of plane relative to earth. Okay, you can easily calculate. So what do you see here? Velocity of plane relative to earth, this one, this resultant vector here, is given by velocity of plane relative to air plus velocity of air relative to earth. Okay, then by using the geometry rules and also vectors, you can also calculate the magnitude of the velocity of the plane relative to earth. So what was the velocity of plane relative to air? 240 km per hour. So due to the wind, velocity is increased. You see 260 km per hour. And here we have alpha. So what is this alpha? The angle between the north and the direction of the plane relative to Earth is given by alpha, and it can be calculated by using this side over this side, okay? In this formula, tangent alpha, or alpha is equal to arctangent 100 km per hour, this side over 240 km per hour. So kilometer per hour will cancel each other. Then the alpha is in degrees, okay? 23 degrees east of north. This is the north direction, and it is 23 degrees east of north. Do you have any question here related to this part? Then let me finish with the final example from the book, correcting for a crosswind. So here this plane is flying from south to the north, but due to the wind, crosswind, it is actually moving from this direction to the 23 degrees east of north, okay? But the pilot would like to keep its direction relative to the ground in this direction towards north. With wind and airspeed, as in example 314, this example, in what direction should the pilot head to travel due north? What will be her velocity relative to Earth? It says that the velocity of plane relative to Earth will be same. Velocity of air, velocity of wind is also 100 km per hour to the east. And now we have different direction for the plane, and then resultant vector will be like this, right? Again, we have a vector addition here. First vector, the velocity of plane relative to air at angle beta, and then velocity of air relative to Earth. This is the resultant vector, velocity of plane relative to Earth along the north, right? So this vector is equal to this vector plus this vector. From the vector addition, you can easily see it, okay? So we have it here. So now just use the relation for this triangle. This is 90 degrees, okay? So everything is given. So by using this relation, square of this one plus square of this one will give you square of this one in terms of magnitude. Then you can calculate speed of plane relative to the Earth, which is given by 218 km per hour. So it has actually higher speed relative to the air, but relative to the Earth, it has lower speed due to the wind, crosswind. And what about this angle? What should be the angle in order to go along this direction? The angle is given by beta is equal to arc sinus 100 km per hour over 240 km per hour. So the result is 25 degrees. Do you have any question here? Okay, then let me finish this chapter. Try to solve the examples and also sample problems at the end of the chapter.